Hello everyone, and welcome back to Tech Adventure. Hope you're doing great and staying sharp in your journey of software development, embedded systems, and interview preparation. In our previous videos, we explored popular communication protocols, microcontroller peripherals, RTOS concepts, top C and C++ interview questions, solid principles, design patterns, and more. If you missed them, I highly recommend checking those out. We have already begun our AI series, starting with the last two videos, where we explored the key concepts of AI, ML, DL, and LLMs. Now, we're going deeper into the AI world, covering topics like LLMs, MCP, edge devices, and more. In today's video, we'll take a deep dive into MCPs, understanding what they are and how they are revolutionizing the AI journey. Let's dive in.
You know how AI is everywhere, right? Generating text, images, even helping us code. But have you ever stopped and thought about how these really smart systems actually talk to the outside world? I mean, not just chatting with us, but connecting to your files, your software tools, maybe even physical devices. It's definitely more complex than just typing in a prompt. Today, we're doing a deep dive into something called the Model Context Protocol, or you'll hear it called MCP. Think of it as like a crucial new language for AI. It's maybe the missing piece that lets these intelligent models truly interact and, do things beyond just having a conversation. So our mission today is to demystify MCP. For you, what is it? Why are people calling it the USB-C for AI apps? And how is it, maybe quietly, powering the next wave of intelligent tools? We're talking desktops, embedded systems, the whole lot. We'll get into the core ideas, look at some real applications, and even peek a bit behind the curtain at how it works.
It's definitely an exciting development. What we're really talking about today, it's like the bridge, right? The thing that lets AI step out of that chat window and actually start reshaping your digital world, maybe even your physical one. AI agents aren't just knowing things anymore. They can do things and crucially do them securely and reliably. It makes AI so much more useful, more versatile, and importantly, more trustworthy. Because you've got clear boundaries and a standard way for it to talk to all sorts of different systems.
Okay, right. Let's unpack that then. If MCP is this vital new language, what does it actually, sound like? How does it give AI those hands and feet you mentioned?
Well, at its core, MCP is an open standard. Its whole job is to let AI applications think LLMs, large language models, connect with external stuff. That could be tools, data sources, different workflows, you name it. And it does this through a really consistent, well-defined protocol.
So that's the USB-C for AI apps thing again.
Exactly. That analogy is pretty good, actually. Once an AI app can speak MCP, it can basically plug into all these different services.
Yeah.
Just like that one USB-C cable connects your laptop to, monitors, chargers, hard drives. It's huge for interoperability.
Okay, so how does that interaction work? Like, who's talking to whom?
Good question. You can basically think of three main players in any MCP conversation. First, there's the host. That's the AI application itself. Could be an AI assistant on your desktop, maybe a co-pilot inside your coding environment, your IDE.
Right.
Second, you've got the client. Now, that's the part inside the host that actually knows how to speak the MCP language. And third, the server. That's any external service or, even a device that wants to offer its capabilities to the AI.
Okay, so the server is like the tool provider.
Precisely. The server exposes things called resources, maybe files or sensor readings. It can offer prompts, which are like structured templates or workflows for the AI to use. And critically, it exposes tools. These are actual functions the AI can call and execute. Think, read this file, or maybe even turn on that light. And they communicate using these structured messages, JSON RPC 2.0 usually. This keeps the dialogue reliable and understandable for the AI. It even handles things like progress updates for long tasks, so the AI isn't just left hanging.
And this isn't just theory, you're saying. It's actually out there being used.
Oh, yeah, absolutely.
Because that's where it gets really interesting, right? Why should you, listening now, actually care about this protocol? You mentioned IDEs.
Yes, think about AI assistants and copilots inside IDEs. MCP is what lets those agents read your project files, run specific build tools, or gather context right there in your development environment. That's a massive step towards having genuinely intelligent coding partners, not just fancy autocomplete.
Okay, that makes sense for developers. What else?
Well, it goes way beyond that. Microsoft is actually integrating MCP support directly into Windows.
Into Windows, wow.
Yeah. So soon, AI applications with your permission, of course, that's key, will be able to interact directly with your file system, other OS features. It really starts to blur the lines between the AI and your everyday computer use. And you see cloud platforms adopting it too. Cloudflare, for instance, uses it so their agents can safely call external apps through this common auditable interface. It actually originated with Anthropic, but its adoption is spreading fast across the whole AI tooling community. It's really becoming a fundamental piece.
Okay, so it's software talking to software mostly. But when you talk about protocols, people, especially maybe folks working with hardware, might think of things like UART or SPI or iQuash. But see, we need to be clear here, right? MCP isn't replacing those, is it? It sounds like it's operating at a totally different level.
That's a super important distinction to make, yeah. And it's a common point of confusion. MCP is an application layer integration protocol. It's designed for high-level software components to talk to each other to get complex jobs done.
Right, software level.
Whereas UART, SPI, iQuest, those are hardware serial buses. They're all about moving raw bits and bytes physically between chips on a board or between boards. They operate at fundamentally different layers in the whole communication stack. It's apples and oranges, really.
Okay, can you break that down a bit more? Like purpose, medium, data.
Sure. So think about the primary purpose. MCP lets AI apps call tools and fetch structured data. UART is for simple point-to-point serial comms. SPI is typically for faster master-slave data transfer between chips. And ICBL lets multiple devices talk on a shared bus using addresses.
Different jobs entirely.
Totally different jobs. And the medium reflects that. MCP runs over any digital transport that can carry its structured messages, network sockets, IPC within a computer, you name it. The hardware buses, they need physical pins and wires.
And the actual information. You said MCP uses structured messages.
Exactly. The data semantics are worlds apart. MCP deals in rich structured messages, function calls with parameters, resource requests, prompt templates, stuff an AI can understand and act on. The hardware buses, they mostly handle raw, unstructured bytes, or maybe very simple fixed format frames.
Okay, and what about safety? Security?
Critical difference number 3. Security and consent. MCP is designed with this in mind. It has built-in guidance for getting user approval, for defining tool safety boundaries, for authentication. This is absolutely vital if an AI is going to interact with the real world or sensitive data.
Right. You don't want an AI accidentally reformatting your hard drive.
Precisely. Hardware buses, being low-level electrical links, have none of that built in. Security is managed way higher up the stack, if at all.
Got it. So different layers, different purposes, different data, different security models. MCP is software integration. The others are hardware communication.
You nailed it. MCP sits above those hardware protocols. It doesn't replace them. In fact, a common pattern is an MCP server acting as a translator. It could wrap, say, a device driver that talks UART or SPI internally. Then it exposes safe, high-level named tools like get temperature to the AI via MCP. The AI doesn't need to know a thing about UART registers or SPI clock speeds.
That's a great way to put it. Like my smart home app doesn't need to know the electrical details of the light switch. It just tells the hub, turn on the light.
Exactly that analogy. The hub handles the low-level stuff. The MCP server does the same for the AI.
Fantastic. So let's talk about where this really shines then. What kind of real-world scenarios, especially maybe in embedded systems or industrial settings or networking, where does MCP really make a difference?
Oh, it unlocks quite a few powerful patterns. One big one is what you could call AI to device, using these safe service wrappers we just discussed. Imagine an MCP server acting like a secure gateway. It exposes specific safe tools, read sensor value, maybe update device firmware. Under the hood, That server can talk to the actual devices using whatever protocol makes sense. Could be UART or SPI for chips, maybe industrial buses like CAN or Modbus, or even network things like MQTT or REST APIs.
So why use MCP as the front door?
Because it gives the AI agent a standard way to first discover what the device can actually do. Then it can request permission from a human if needed for sensitive actions. And finally, it executes these standardized tool calls, all with proper auditing and clear error handling built in. It standardizes the interaction.
Right, discovery and control. What else?
Think about fleet operations or observability copilots. An MCP-enabled AI agent could tie into all your monitoring systems, your device registries, maybe your ticketing system. It could look at complex alerts across hundreds or thousands of devices, maybe summarize them, suggest solutions, or even call pre-approved tools to, say, rotate security keys or push out a new configuration.
Wow, managing large-scale systems.
Exactly. It standardizes how the AI talks to all these different back-end systems, monitoring tools, CMDBs, ticketing platforms, all through one agent, again, with proper consent and safety checks.
That sounds incredibly useful for complex environments. What about developers, firmware engineers?
Yeah, absolutely. You could significantly enhance the developer workflow, especially around firmware development or hardware bring-up. Imagine an AI right inside your IDE. Using MCP, it could securely read files from your code repository, pull up relevant hardware data sheets, maybe even help generate register configurations. Or it could call local command line tools that you use every day, like firmware flashing utilities or unit test runners. MCP provides that unified way to integrate the AI with your code, your docs, and your local tools. Microsoft's work on Windows MCP support is really aiming at this kind of local, powerful integration.
Okay, that's compelling. Any other big areas?
Definitely see potential in network operations centers, NOCs, and security operations centers, SOCs. An MCP agent could connect to your ticketing system, your CM, your network management system, config stores, run books, all the tools analysts use. It could help draft incident notes based on alerts, suggest firewall rule changes, or even execute controlled remediation scripts via approved tools.
Again, it's that standardization across potentially many different vendor tools.
That's the key benefit. Instead of writing custom API integrations for every single tool the AI needs to talk to, you potentially just need MCP servers for each one.
So it reduces that integration burden significantly. But I mean, is it realistic to think everything will just support MCP out of the box? There must be legacy systems or tricky APIs.
That's a fair challenge. No, you won't find MCP support everywhere overnight. There will definitely be cases where you need to build an MCP wrapper or server for a specific legacy system or a proprietary API. But the beauty is you only need to build that wrapper once. After that, any AI application that speaks MCP can interact with that system through your wrapper. The effort shifts from potentially N different AI integrations down to just one MCP server per system.
Okay, that makes sense. Build the bridge once. And security must be paramount in these NRC SOC or fleet scenarios.
Absolutely critical. And the MCP specification emphasizes things like user consent loops, requiring explicit approval before certain actions are taken, and the principle of least privilege. You design your MCP server to only expose the necessary safe tools. You wouldn't just expose raw, dangerous device controls without serious guardrails and approval flows.
And where do these MCP servers typically run? On the device? In the cloud?
It's flexible, really. It depends on the use case. It could run locally on a developer's machine for IDE integration. It might run on an edge gateway device sitting close to the hardware it controls. Or it could run in the cloud for managing large fleets or integrating with cloud services.
Okay, so MCP really expands what AI can do. It's like giving it this universal remote. But how does it actually work under the hood? Let's get into the structure bit. How are messages framed? How does it stay reliable?
Yeah, let's dig in. It's actually quite elegant in its design. MCP doesn't try to reinvent the wheel for basic data transport. It relies on existing digital channels, TCP connections, WebSockets, even simple standard input-output between processes.
So it rides on top of standard communication methods.
Exactly. The real magic is how it structures the information within those channels. MCP uses a specific message framing technique. Each message sent is a complete, self-contained JSON object. And critically, before each JSON message, it sends a content-length header, telling the receiver exactly how many bytes the following JSON message will be.
So no ambiguity about where one message ends and the next begins.
Precisely. Think of it like digital punctuation. It ensures the receiver reads exactly one complete message at a time, even if data arrives in chunks or if multiple messages are sent back to back. This is crucial for avoiding misinterpretations, especially when large amounts of data, like tool results or context, might be flowing.
Okay, content length plus JSON. What's inside that JSON?
It uses the standard JSON RPC 2.0 format. So you have fields like JSON RPC, always 2.0, and EAD to match requests with responses, a method specifying the action, and params holding the input data. Then responses have either a result or an error field.
Standard stuff for remote procedure calls.
Right. But MCP adds its own specific extensions on top of that foundation. This includes things for capabilities negotiation, where the client and server tell each other what MCP features they support right at the start of a session. It also defines resource descriptors, metadata about files or data sources, and crucially, tool descriptors.
The definitions for the tools the AI can call.
Exactly. These descriptors define the tool's name, its input schema, its output schema, and even human-readable documentation explaining what it does and how to use it safely.
Why is that so important?
Because it makes MCP self-describing. The AI host doesn't need to have prior hard-coded knowledge about every single tool it might encounter. It can connect to an MCP server, ask what tools do you have, get back these rich descriptions, validate the inputs and outputs, and then dynamically call the tools.
That makes it incredibly flexible and adaptable for the AI. Okay, so that's the structure. How does it handle, like, keeping track of multiple things happening at once? Synchronization.
Right. Synchronization here isn't about clock timing. It's about coordinating requests and responses, especially when things might be happening asynchronously or across a network. The key is that unique ID field in the JSON RPC messages. Every request has one, and the corresponding response must have the same ID. This allows the client and server to perfectly match replies to their original requests, even if multiple requests are sent out and responses come back in a different order.
So it handles out-of-order responses naturally.
Correct. MCP also explicitly supports streaming and progress updates. If a tool call might take a long time, maybe processing a large file or running a complex simulation, the server doesn't have to wait until the very end to reply. You can send back intermediate progress notifications, maybe like event.progress %.42. This keeps the AI informed, prevents timeouts, and makes the user experience much better.
That's smart. Avoids the AI just sitting there silently.
Yeah, and all this, the request response pairing, the progress updates, the initial capability negotiation contributes to maintaining a robust, stable session state between the AI and the server, even when complex, long-running, or parallel tasks are involved.
Okay, so it sounds well structured. What about when things go wrong? Network glitches, corrupted messages. How reliable is it?
That's a good point. For low-level error detection, like catching corrupted bits during transmission, MCP generally relies on the underlying transport layer.
Yeah.
So if you're using TCP, TCP's built-in checksums handle detecting basic transmission errors. MCP doesn't reinvent that.
Okay, it trusts the layer below for basic integrity.
Right. MCP's focus for reliability is more on the structured level. Can the received data be parsed as valid JSON? Does the message conform to the JSON RPC 2.0 structure? If it's a tool call, do the parameters match the tool's advertised schema? Does the server actually support the requested capability?
So catching logical errors in the conversation itself.
Exactly. If a message is malformed, bad JSON, content length mismatch, the framing layer will detect it and typically reject it or close the session. If the JSON is valid but the content doesn't make sense according to the MCP rules or the negotiated capabilities, you'll get a structured JSON RPC error response back.
What about retries if a message just gets lost?
Well, again, if you're using a reliable transport like TCP, message loss is usually handled by TCP's retransmission mechanisms automatically. If the whole connection breaks, the client will detect that and typically try to reconnect and potentially reestablish the session. For application-level retries, the ID field is key. A client sends a request with an ID. If it doesn't get a response with that same ID within a certain timeout, it knows something went wrong. It can then decide whether to retry, perhaps based on the type of operation, or specific error codes if it did get an error indicating a temporary issue. MCP provides structured error codes to help guide this retry logic. Makes sense.
So let's imagine a complex scenario. An AI is talking to multiple MCP servers simultaneously, maybe GitHub, a database, Slack, like you mentioned. How does MCP keep those conversations separate and reliable?
That's where the session-based nature and the framing really help. The AI host establishes an independent MCP session with each server. Each session runs over its own transport connection or logical channel.
So separate pipes.
Separate pipes, exactly. Each pipe has its own independent message framing using content length, its own sequence of JSON RPC messages with their unique IDs within that session. This provides error isolation. If the connection to, say, the database server fails or starts sending garbage, it doesn't affect the ongoing conversations with GitHub or Slack. Those other sessions continue normally.
That's crucial for building robust systems where one faulty component doesn't bring everything down.
Absolutely.
Yeah.
It allows for graceful degradation. The AI might lose access to the database tools, but it can still interact with code repositories or send notifications.
Okay, so it's robust, handles errors well, keeps conversations separate. How does it manage performance, especially with all these potentially concurrent conversations? How does it keep things moving fast?
Performance is definitely a design consideration. Because MCP allows for multiple independent sessions, and because JSON RPC with its ID field allows for asynchronous request response handling, an AI host can achieve high concurrency. It can send out multiple requests across different sessions, or even multiple requests within a single session if the server supports it, without waiting for each one to complete sequentially.
So parallel processing of AI tasks.
Pretty much. Responses can come back whenever they're ready, and the host uses the ID to match them up. This parallelism is a huge advantage compared to older, strictly synchronous or single-channel protocols. It lets the AI do more, faster, without getting bottlenecked, waiting for one slow operation.
How does it handle things like bandwidth? Does MCP try to manage that?
Not directly, no. For bandwidth allocation and flow control, MCP again relies on the underlying transport layer, typically TCP's mechanisms for congestion control and windowing. At the application level, though, strategies can be implemented. The AI host might prioritize sending requests for user-facing tasks over background operations. An MCP server could implement rate limiting to prevent being overwhelmed by too many requests from one client. You might also use network-level quality of service, QoS policies, if you have multiple MCP streams competing for bandwidth on a shared link.
Right, standard network management techniques apply. What about deciding which request gets processed if multiple arrives at roughly the same time? Is there arbitration?
Yes, but channel arbitration in MCP isn't like, say, ISAN-SC where devices electrically negotiate for bus access. It's more logical. Within a server handling multiple requests, it comes down to how the server queues and processes incoming messages identified by their JSON RPC IDs. Servers might indicate during capability negotiation whether they can handle concurrent tool calls or if they process them sequentially. The AI host also plays a role in arbitration by deciding the order and priority in which it sends requests across its various active sessions. It can prioritize urgent tasks based on its internal logic or user interaction.
So it's a combination of server capability and host-side policy.
Exactly. It ensures resources aren't overloaded, provides a degree of fairness, and lets the AI prioritize what's most important at any given moment, keeping things responsive.
This has been a fantastic look at the protocol itself. Now, let's shift gears a bit. For the builders, the engineers, the curious folks listening, how would you actually implement this? Let's say on something small, like an STM32 microcontroller. How do you get a tiny chip speaking this sophisticated AI language?
That's a great practical question. The core idea, remember, is that MCP is fundamentally about exchanging structured JSON messages over some communication channel. So on an MCU like an STM32, you need basically three components in your firmware. First, you need a transport mechanism that could be a UART serial connection back to a PC, maybe a USB acting as a virtual COM port, or if your STM32 has it, an Ethernet connection using TCP/IP.
Okay, the physical pipe.
All right. Second, you need a lightweight JSON parser and serializer library. There are several good ones written in C suitable for microcontrollers, like CJSON or JSMM. Their job is to convert the incoming byte stream into a data structure your C code can understand and format your response back into a JSON string.
Got it. Parse the message, build the reply.
And third, you need the request dispatcher logic. This is the core of your MCP server on the MCU. It looks at the parsed JSON request, figures out the method being called, like tools call, extracts the params, and then maps that to an actual function in your firmware, maybe addcred or GPOset.
So it translates the MCP tool call into a local hardware action.
Precisely. The flow would be initialize the communication peripheral, UART, USB, ETH, continuously read incoming data using the content length header to frame complete JSON messages, parse the JSON, dispatch the request to the appropriate local function, get the result from that function, build the JSON response message, including the original ID, send the content length header, and then the JSON response back over the transport. Doing this effectively turns your little STM32 into a lightweight MCP server, exposing its specific hardware capabilities as callable tools.
And what specific hardware registers or peripherals on the STM32 would be involved in making this happen? Does MCP define new hardware needs?
No, MCP itself doesn't define any new hardware registers. It's purely a software protocol definition. It relies entirely on the existing communication peripherals that microcontrollers like the STM32 already have. So you'd be configuring and using the UART registers for serial communication, setting baud rate, enabling TXRX, handling interrupts, or the Ethernet MS registers and maybe DMA for network communication if you're using TCP/IP, or the USB OTG core registers if you're using USB Virtual COM. You'd likely use DMA, direct memory access controllers, for efficient data transfer between peripherals and memory, reducing CPU load. You might use timers for handling timeouts, for instance, waiting for a complete message, and you'd heavily use the NVIC, message vectored interrupt controller, to handle interrupts from the communication peripheral, signaling new data arrival or transmission completion.
So it's leveraging all the standard comms infrastructure on the chip.
Exactly. The STM32 peripherals provide the pipe, and your firmware implements the MCP language spoken inside that pipe using JSON.
How does this change if you're using a real-time operating system like FreeTOS on the STM32?
An RTOS like FreeTOS actually makes implementing this kind of thing much cleaner and more robust. You typically divide the work into several concurrent tasks. For example, you might have one task dedicated to handling the low-level communication receiving bytes, framing messages using content length, and maybe putting complete messages onto a queue.
Okay, a dedicated comms task.
Then another task, the parser task, could wait on that queue, pull off complete messages, parse the JSON, validate the request structure. If it's a valid tool call, it could then maybe put the request details onto another queue for a specific worker task. You might have different worker tasks for different types of hardware, an MCP pad task, an MCP GPO task, etc.
Specializing the work.
Right. That worker task performs the actual hardware interaction, reading the ADC, setting the GPIO. Crucially, it would use RTOS semaphores or metexes to safely access the shared hardware resource if other tasks might also need it. Once the worker task has the result, it could set it to a final responder task, maybe via another queue. This task formats the JSON response message and sends it back out through the comms task.
So the RTOS helps manage concurrency, resource sharing, and message passing between the different stages.
Precisely. Using RTO primitives like tasks, queues, semaphores, and timers makes the whole system much more modular, scalable, and easier to manage than trying to do everything in one big loop.
Okay, last question on the practical side. How do you debug this stuff when it inevitably goes wrong?
Debugging communication protocols always involves looking at different layers. If you're using UART, you might start with an oscilloscope to just check the electrical signal levels and timing. Then you'd likely use a logic analyzer, maybe something like a Saley logic analyzer.
Right, those are handy.
They can decode the UART stream live, showing you the actual bytes being sent. You can verify the content length framing is correct and see the raw JSON text. That helps isolate if the problem is in the electrical transmission, the framing, or the JSON content itself.
And for Ethernet?
For Ethernet TCP, the go-to tool is Wireshark. You capture the network packets, filter by the IP address or port number used for your MCP connection, and Wireshark can show you the reassembled TCP stream. You'll see the content length headers and the full JSON request and response messages directly. You can check if the JSON is valid, if the IDs match up, if the content makes sense.
So standard tools for the transport layer, basically.
Exactly. Debugging involves checking the physical transport layer, oscilloscope, logic analyzer, Wireshark, then the framing layer, is content length correct? Then the syntax layer, is it valid JSON? And finally, the semantic layer, does the MCP message make sense in the current context?
You combine these hardware network tools with your standard firmware debugging tools like print statements or a debugger connected to the MCU, perhaps looking at RTOS task states and queue contents. That's a great breakdown. So stepping back then, what does this all mean for you, the listener? MCP really feels like much more than just another spec sheet. It seems like a truly foundational piece for how AI is going to weave itself into our digital and maybe even physical world. It's making AI more connected, more capable, and hopefully more helpful across just a huge range of applications. It feels like the silent enabler, doesn't it?
I think that's a perfect way to put it. It is that standardized, scalable, and reliable protocol that bridges the gap. It connects those incredibly intelligent AI models we're developing with the actual real-world tools, the data resources, the hardware that we use every single day. It's really what gives AI the hands and feet it needs to move beyond just generating text or images and actually interact with and manipulate our environments.
So as AI keeps evolving at this incredible pace, just imagine the possibilities when potentially every device, every piece of software can securely expose what it can do using this common, universally understood language. Think about this. Today, AI might help you write some code. With MCP becoming widespread, that same AI could potentially help you debug the hardware the code runs on. It could flash the firmware to a device sitting on your desk, maybe even coordinate a software update across a global fleet of devices, all through a consistent, secure interface. It really shifts the role of AI from just an assistant to potentially an active operator, an active participant. So the question for you is, how will you leverage this newfound connection? What problems could you solve when AI can safely and reliably interact with anything? What will you build? Thanks so much for joining us on this deep dive into the Model Context Protocol. We really hope you feel better equipped now to understand this fascinating and I think really important development in the world of AI.
Thank you for watching. Please like, share, and subscribe to our channel for more exciting updates. Your support motivates us to create valuable content. Share your feedback or topic requests in the comments. See you in the next deep dive learning or interview session.